So, as a geotechnical engineer, you might not always get an opportunity to construct always on flat ground, isn't it? There will be a lot of challenging situations where the ground on which you're going to build or the ground beside you is sloping or maybe unstable, or when many people might have observed large scale landslides and everything, landslides, mud flows and everything in the recent 2020 and 2018 floods and heavy rainfalls in Kerala also. uh, Everyone, I'm sure that everyone in Kerala have seen that, and at least most of you might have seen videos at least of large scale landslides and disasters that happened in Kerala in the past 1 or 2 years. So this mostly happens in all these hilly areas, hill stations, and people from Tamil Nadu also. You might have seen this in the Nilgiris district, especially Ooty and all. You might have seen a lot of places where the land has slided down and has caused extensive damage. So, most of these cut roads, if you go to Uti or Munnar, most of these roads, you might have seen that there are a lot of retaining walls on the roadsides, isn't it? Because one side of the road will be a cliff. I mean, the road will be on a cliff, and one side of the road will be a, you know, uh, will be construct, but one side of the road will be a slope on which the soil has to be retained so that it doesn't slide down and cause problems to the traffic. So and another thing is that you might have to construct on these sloping grounds where the soil might be unstable in the case of surface flows or drainage or runoff. Right? So in all these conditions, these are all challenging situations for a geotechnical engineer. And not just in the case of constructing anything on the slope, but also if you are living someone, if you're a person who's living near a hill or a slope, there are chances for the slope to slide down and cause some danger to him, right? So in all these cases, it's the uh, responsibility of a geotechnical engineer to ensure this safety. You have to make sure that your slope is stable and it is safe from sliding down and causing any disaster in a later stage, right? So for this, you have to understand the concepts of slope stability, and you have to understand what are the causes behind it. You have to understand how to prevent it, or how you can avoid it. So these things you should understand. You should understand the concept behind it. You should understand how to evaluate the factor of safety against slope failure, and then you can think of remedial measures for the same, right? So, so what is a slope? It's a very simple explanation. It's just what's an earth slope? It's an unsupported inclined soil mass surface, isn't it? Very simple explanation. So it can be natural or man-made. So highway sites, railway sites. You might have seen even in Etimadai, when you walk from our campus gate to the to Etimadai railway station, you can see that the railway tracks lie on an embankment, isn't it? It has, the railway track has sloping sides on either ground, isn't it? So that's also a slope. So sometimes there we have stable ground, so sometimes you have to raise it further, so you have a sloping ground on either side of the railway track. You have seen that, obviously, isn't it? So highways are also like that. So highways, railways, then embankments, earth dams, canal banks, etc., all of these are man-made slopes, isn't it? Then, so when does this fail actually? So you can say that the soil mass has failed when this large mass of soil, it slides or slips along a plane or a curved surface, isn't it? You might have observed a landslide. Everyone have seen a landslide, at least in photos. I think everyone have seen it, isn't it? So you might have observed that a large mass of soil has slided down. Uh, it has slipped down along a plane or a curved surface. You might have observed that the uh, soil has slided down, and behind that you might have seen a exposed ground surface, isn't it? So that surface is your curved surface of the plane along which the soil has slided down, right? Usually that soil mass, it actually moves outwards or downwards away from the sloping surface, mostly due to gravity, right? Mostly due to the sulfate of the soil, it slides down. So it slightly moves outward. The soil mass moves outward or downward away from that sloping surface. And this natural slope failures, obviously it's called landslides. Everyone have seen that. Here's a natural slope. So you can see in this image, it's a natural slope. So will you right away go ahead and construct a large structure here? No, right? You have to think twice, isn't it? This, I guess everyone have seen or experienced something like this, especially if you go to Munnar or Uti, Kodaikanal, wherever all these ghat roads, you might have experienced this, isn't it? One side of the road, you might have seen heavily sloping ground, right? So these are all natural slopes, but retained by man-made structures like this, isn't it? They are stabilized so that they doesn't slide down and block these roads, right? Here you can see very extensive slopes on the sides of the railway tracks. This is opposite of the case that I was mentioning earlier, what we see in Etimadai. In that case, the railway tracks are elevated on an embankment, which has sloping sides on both the sides. But in this case, this is the opposite. You can see here. The railway tracks lie between two slopes. So you have to ensure that these slopes are stable and it doesn't slide out, the soil doesn't slide down onto these tracks and cause some disastrous damages, right? So these slopes are also to be stabilized, right? Then canal sides, you can see here, this also has to be stabilized and to prevent sliding into this canal, right? Dams, you can see here, dam sides of the dams, they are also steep slopes. You have to make sure that they doesn't slide down and cause the collapse of this dam, right? Everyone have experienced a man-made slope and a natural slope at some point of their lives, right? All of you. So I mentioned earlier, you might have observed, I'll show you a failed, so here you can see, this is how a landslide occurs. You had stable ground here, but this soil mass have slided down. It has moved outward and downward, as we mentioned earlier. It has moved downwards and outwards, right, along a particular plane or a curved surface. You can see here on the cross section, you can see this curved surface along which that failure has occurred, isn't it? So that this surface, ground surface, has been exposed, correct? So you can see the soil mass was stable earlier, then it has moved downward and outward, exposing this ground surface. So this surface is my plane or the curved surface or the plane along which the failure has occurred, right? So that surface along which the soil mass slides when soil failure occurs is called the critical surface of failure. So as you can see here, this surface, this is my CSF or critical surface of failure. That is the surface along which failure or the sliding of the soil mass occurs, right? When does this occur basically? In simple term, if you want to explain the concept to someone, you can say that when the mass of the soil, right, the force caused due to mass of the soil, right, that force, the driving force, I call that the driving force, is greater than your resisting force along the surface, correct? Right? So the whole soil mass here, it is held together due to some resisting force between the soil particles, right? What are those resisting forces, or what gives soil its strength and stability? So the soil gets its strength from cohesion and angle of internal friction, C and phi. We saw in shear strength, isn't it? So that C and phi keeps the soil intact, and when the force due to this soil mass, right, the force due to this soil mass, the driving force, if that force is greater than the C and phi mobilized along this surface, the strength of the soil, that is the resisting forces along the surface, if it is less than the driving forces due to the soil mass, then this will slide down, isn't it? You can see behind that, the soil behind this, in this soil, within the soil, the resisting forces, that is the strength of the soil, the C and phi of the soil, can withstand the forces acting due to the soil mass here. That is why this is staying stable here, right? But in this case, the soil mass here along this CSF, that is a critical surface of failure, along this surface, the driving forces or the driving moments are greater than the resisting moments, that is the strength of the soil along this plane. That is why it is going to slide along this particular plane. So why exactly did it slide along this particular plane itself? I've told you no chain is stronger than its weakest link, isn't it? So similarly, in this whole soil mass, there might be some point where it is the weakest, right? So this plane might have been the weakest, or there might have been discontinuities, or there might have been points within this soil mass where the strength is less. So along that point, it might have started rolling down, because along that point, maybe your C and phi was not sufficient to hold this large soil mass, right? So it might have slided down, right? So when the forces causing the slip or slide is greater than the forces restoring or stabilizing the slope, that is the forces that resist movement of the soil mass along the critical surface of failure, when that forces causing slip or slide, or the driving forces or driving moments, if they are greater than the restoring or resisting forces, then along that critical surface of failure, the slope will slide down, right? So that failure occurs due to what? Why does this soil mass slide down? So when there is gravitational forces acting on the soil mass which tries to pull it down, what is resisting it actually? Cohesion and C and phi is resisting it. But when this gravity acts along that critical surface of failure, when that gravitational forces along the critical surface of failure is higher than the resisting forces in that soil, then it can slide down. So one reason is gravitational forces. Anything else? One more reason? Water table, isn't it? Water, groundwater is a major problem for all civil engineers, all geotechnical engineers, isn't it? Because a lot of issues are there due to groundwater. We discussed that during soil investigation, isn't it? Groundwater table in the soil can cause a lot of problems. So here also, if you have water in the soil, seepage forces. Do you remember the flow nets? So if you have different potential, you could create equipotential lines and flow lines and etc. Right? And what did those flow lines represent? The path the water particle will take through the soil, isn't it? As it drops its potential, as it loses its potential, it flows and it loses its potential, right? And using these flow nets, we could calculate many parameters. Isn't one major parameter in that was our seepage pressure, isn't it? Do you remember? So that seepage pressure also tries to exert. The seepage pressure is some pressure exerted by the water in the soil uh, against the uh, retaining forces of the soil, isn't it? These forces also try to push this soil out, isn't it? Imagine the groundwater table is here. So the potential will be high here, and this is an open surface. The potential will be low here. So obviously the water will try to flow towards this direction, isn't it? So at any point within the soil mass, there can be seepage pressure which tries to push the soil mass outwards. Agree? Do you remember the equipotential lines and flow lines and calculation of seepage pressure? At any point within the soil mass, we could calculate the seepage pressure. Do you remember? So that water particles will always try to move out, and that water particles will exert some forces on the soil mass, right? They will try to push the soil mass outwards. Another problem, if there is water in the soil, anything else that you can relate to the slope stability, something related to MDD-OMC curve, the particles rearrange themselves into a more dense configuration. So when you added water, what was the advantage in that condition? When you added water, the particles got lubricated and they could slide over each other very easily and rearrange themselves, isn't it? Right? So the particles can get lubricated and they can roll over each other more easily. The friction was reduced, isn't it? Friction between the particles got reduced as they got lubricated. So same concept can be applied along the critical surface of failure as well, right? If there is a lot of water in the soil mass, the particles are lubricated and they can roll over each other more easily, isn't it? So that's also a concern, right? So the slope failure can occur due to two things. One is due to gravitational forces and the other one is due to water in the soil. The contributing parameter is by seepage forces within the soil mass, isn't it? Right? So these two parameters causes failure of a slope, gravitational forces and seepage forces within a soil mass or water in the soil. Also, when you add water into the soil mass, another parameter that increases here is its overall density. Saturated density is greater than dry density, isn't it? So if the voids are filled with water, obviously the mass of the soil mass also increases. So obviously your gravitational forces are also going to increase. Agree? Right? More saturated soil, more density means the mass of the soil mass is going to be higher, and obviously the gravitational forces are also going to be higher, correct? So water in soil is also a problem here. So what resists that failure? Obviously the shear strength or the frictional force, depending upon the type of soil. Shear strength or frictional force, I would say cohesion and or frictional force. Okay, it's not shear strength. Cohesion, or basically shear strength of the soil, or you can say cohesion and or frictional force. So why I mentioned and or here? Because if it is a C5 soil, it will have, I'll correct it now. It's some soils will have cohesion, purely clay soils will have cohesion, purely sandy soils will have friction. So if it is a C5 soil, normal soil, it's having clay and sand in it, so you will have cohesion and frictional force both. So basically shear strength of the soil will resist that movement, right? So failure occurs due to gravitational forces and seepage forces, and forces resisting that failure is cohesion or the frictional force or both. So basically the shear strength of the soil, right? So the seepage forces, how can you calculate the seepage forces? Basically from flow nets, right? You have done a lot of problems where you calculated your seepage pressure. So I guess you remember that. So seepage forces can easily be computed from flow nets. And how do you calculate your shear strength of the soil? So basically from Moore Coulomb theory, isn't it? Right? So from Moore Coulomb concept, you can calculate your C and phi parameters, and from flow nets, you can calculate your seepage pressure, and simply by calculating the area and multiplying it with the density of the soil, you can calculate your weight of the soil mass, and you can find out the forces due to gravity, right? Weight of the soil mass, that also you can easily calculate. So you can easily find out your driving forces, and you can easily calculate your resisting forces, right? So that lays the uh, basic foundation or concept behind slope stability issues. Okay, so we will see how to calculate these and how to find out this critical surface of failure using different methods in this chapter. Okay, this is an actual image of landslide here. You can see the road was here, the whole soil slided down. You can see what is this surface called? Critical surface of failure, isn't it? It's a plane or a curved surface, right? Along which the soil must have slided down, right? There are basically two types of slopes. So to go ahead with the concepts behind slope stability and deriving the factor of safeties, we have to consider or classify soils into soil slopes into two types. So one is an infinite slope and another one is a finite slope. So infinite slopes, it's a it represents a, you can see here, infinite slope. You have a semi-infinite soil slope. It is bounded only on the top surface, and below that it extends infinitely. Okay, this surface extends infinitely, and below the soil extends infinitely. It is bounded only by the ground surface. Right. So this is called an infinite slope. So it represents a boundary surface of a semi-infinite soil mass inclined to the horizontal, as you can see in this figure. Semi-infinite soil mass, I told you, it is infinite in this direction downwards, and it extends infinitely on both directions. It's bound only by the ground surface. That's why I say that it is semi-infinite soil mass. Okay, so it's a semi-infinite soil mass which has a boundary surface, as you can see here, right? There's a boundary surface inclined to the horizontal, having constant soil properties for all identical depths below the surface. All right, so you yeah, consider homogeneous soil properties for different depths. So from, as you can see here, this particular soil, throughout this strata you have homogeneous soil properties, below that another strata, throughout that strata you have homogeneous properties. All right, so this sloping surface, it is inclined to an angle to the horizontal, and it extends infinitely. Okay, so basically practically slopes are never infinite, but if the height of the slope is very large, if it extends for a very large length, it is considered as an infinite slope. Okay, And another thing is that you have different strata in soil. All these strata boundaries, they are also assumed parallel to the surface. Okay, this is my surface. You have the next soil strata. This is assumed parallel to the ground surface itself. Okay. Also, the slip surface is also assumed parallel to the slope surface. So if this is the slope and this is, if this is your CSF, that CSF is also assumed to be a plane which is parallel to the ground surface. Is it clear? This is a infinite slope. Okay, this is more or less conceptual. Okay, then we have a finite slope. So it's a slope of limited extent. You have a base and a top surface, and you have heterogeneous soil properties at identical depths. And here the slip surface is curved. So inclined face of embankments, earth dams, cuts, etc. are all finite slopes. As you can see here, you can see that the slope is finite. You have a top and a base. This is of finite extent. It's not extended. The slope is not extending infinitely. So you can see that this dotted line was actually my actual slope. But once it failed, you can see that the failure has occurred along a curved surface. What is this surface called? Critical surface of failure, CSF. All right. So you can see that the soil has moved outwards and downwards, and it has failed along a curved surface. But in the case of infinite slopes, we assumed that the CSF is parallel to the slope surface. Okay, and the uh, soil is extending infinitely in all directions and is bounded by the top. But here the slope is bounded at the base and the top. The soil slope is finite and the failure surface is expected to be curved, as you can see here. Right? Common examples: face of embankments, dams, cuts, etc. Okay. Let us try and derive the expression for factor of safety of a infinite slope first. Okay. So you mark your ground surface. This is my ground surface, sloping ground surface, infinite. So it's AB. It marks the ground surface. And imagine CD is my CSF. Okay, critical surface of failure. Okay. So I am imagining a block of soil here of width B. Okay, width B on the ground surface. Imagine a soil mass of width B on the ground surface and assume that the critical surface of failure lies at a depth Z from the ground surface. All right, this is my initial conditions. Okay, AB is my ground surface, CD is my critical surface of failure which lies at a depth of Z from the ground surface, and imagine a soil mass, a soil wedge of width B on the ground surface. Okay, so considering this soil mass, due to this soil mass, the forces acting, the normal stresses acting on the critical surface of failure is sigma z. At a depth z, the normal forces acting on this surface is sigma z. This is my initial condition. Okay, and I is my angle at which the surface is inclined. Okay, so if I resolve this force sigma z, I'll get this two components, tau and sigma in soil, right? So you can see sigma z acts downwards at an angle inclined at I. I have my sigma normal stress, and this part represents my shear stress tau. So sigma and tau on a plane of soil mass. We saw this in shear strength, right? Similar. So I have sigma z, normal stress acting on the surface CD at a depth z, and I resolve it into sigma and tau. All right. So this angle is I. Right. So I can say that this sigma, if I consider this triangle, I can say that my normal stress here, resulting normal stress here is sigma z into cos I, right? And tau is equal to sigma z into sin I. This tau is equal to sigma z into sin I, and this sigma is equal to sigma z into cos I. This is my initial condition. All right. Consider this prism or this soil mass. So the length of the prism actually here is B into cos I, isn't it? Because this angle is I, right? This angle is I, the slope of this angle is I. So this length is nothing but B cos I, because this is 90 degree. This angle is I, this length is B. So this horizontal length is actually B cos I, correct? And volume per unit length. So this is my depth of the soil, and imagine into this screen I have the length of the soil, right? Into the screen in Z direction I have the length of the soil mass. So volume per unit length, so I am assuming unit length here, right? So if I am assuming unit length, what is the volume per unit length here? B cos I into Z into 1, right? 1 is along the screen, right, into the screen. That is how the length of my soil slope is like. Okay, so I am considering unit length here. So it is volume of this prism is, or soil mass is, B cos I Z into 1. So what is the weight of this prism? So if the unit weight of the soil, bulk unit weight of the soil is gamma, then weight of this prism W is equal to nothing but B cos I Z into gamma, correct? Very simple, isn't it? Gamma into B cos I into Z, correct? So what will be this normal stress? Sigma Z, weight by area on which it acts, isn't it? So that will be W by B into 1, because I am talking about this direction into the screen, right? So unit length. So W by B, I have my sigma Z. And what is that W? Gamma Z B cos I. So divided by B, I get sigma Z is equal to gamma Z cos I. Correct? And previously we resolved this sigma as sigma is equal to sigma Z cos I. Sigma Z cos I is equal to sigma, and tau is equal to sigma Z sin I, right? So if sigma is equal to sigma Z cos I already derived that sigma Z is equal to gamma Z cos I. So sigma is equal to gamma Z cos I into cos I. So I have my sigma normal stress on this surface as gamma Z cos square I, correct? And similarly, tau is equal to sigma Z sin I. I saw that earlier, this one, resolving this triangle. So tau is equal to sigma Z sin I. So here tau is equal to sigma Z sin I, and sigma Z is gamma Z cos I. So basically my tau is equal to gamma Z cos I sin I, right? And what is my tau F, shear strength of the soil that resists this stresses? It is C plus sigma tan phi, right? So the driving stresses here is basically this tau, and the resisting stresses here is basically shear strength of the soil, tau F. So if to calculate the factor of safety of this slope, factor of safety against failure of the slope, it's basically tau F by tau, isn't it? The resisting forces by driving forces. That ratio gives my factor of safety against sliding of this soil mass along the surface CD. Clear? Hope it's clear. Very simple derivation, isn't it? Very simple. If you could just resolve this cos and sine based on these angles, nothing else. Very simple. So factor of safety against sliding is resisting forces by driving forces. So tau F by tau. I think we will stop here, and tomorrow we will start deriving these expressions. Factor of safety, expression for factor of safety for cautionless soil or clay soil, sandy soil, and C5 soil. For these different types of soil, what is the expression for factor of safety in the case of infinite slopes? We will see tomorrow. Okay, we will wind up for now.